Hey Maura, what's up? Hope you're feeling better. So this will be a quick little thing here. Like I said, print out the first 3 pages of the notes. If you haven't yet, you should do that. You can pause this and do that. If you have them ready to go, this is our new unit on momentum and impulse, and it's one that people do pretty well on. So the fact that you missed a few days already shouldn't put you at too much of a disadvantage, I don't think. All right, and like we said, we'll get that lab done when you get in here. So the a lot of concepts, ideas in physics have good definite definitions, and momentum isn't really one of them. This is a little nonsense thing, but sometimes you see some of these sort of nonsense definitions of momentum, but we want to get down to what it really is. So here's a couple of examples to help you think about it. First, this is a little bit gruesome. Yeah, we have a dump truck and a girl on a tricycle, and forget about them riding in the truck running over the girl. But the question is, which one do you think had more momentum, truck or tricycle? And notice they were moving at the same speed. Any guesses? Well, it's the truck. All right, truck has more momentum. Again, assuming it's at the same speed as something else. So why? Well, hopefully we can get the idea that more mass equals more momentum. And this is pretty cool, by the way, don't you think? I'm talking, I'm writing, you see it all happening. Right. Yeah, question 2. This one's the graphic nowhere near as fun. Which has more momentum? This ball or this ball? The one that goes fast or the one that goes slow? Which one do you think has more momentum? Well, hopefully we can get to the idea that this one has more momentum. Ball moving fast. And the y there's the y. The y there is, I'll say, higher velocity, or really a faster speed, sort of same thing, equals more momentum. Now notice we're trying to make the point that this thing's mass is the same as this thing's mass. All right, just like on the first example up here, we were trying to be sure that we're talking about two objects that are moving at the same speed. All right, so if we tie these things together, we come up with an equation for momentum. Now, momentum, the symbol we use is, you can use a lowercase p. I use, if we're writing it, it's called a rho, a Greek rho. So it's kind of like p. So if you want to just write a p, that's fine. So we say that p is m times v. All right, where m is mass, v is velocity, and p is momentum, or rho is momentum, whatever you want to call it. All right, real important thing, velocity is a vector, and therefore momentum is a vector. All right, directions of things that happen with momentum questions are really, really important. Okay, and so that's, we started this talking about what's the definition of momentum. Well, this is actually the definition. When you in a good definition, when you look it up, it says momentum is the product of an object's mass and velocity. That's the actual definition. Trying to get fancy with ideas and concepts doesn't really help much here. That's it. That is what momentum is. Units, well, since momentum is, I'll just write it again, mass times velocity, its units must be the units of that. Units of mass are kilograms. Units of velocity are meters per second. So we usually just write that as kilogram meters per second. All right, no need to get fancier than that. Couple of easy examples, right? Here's example 1. We have 4 kilogram, that's mass. Ball rolling to the right at a speed of 12 meters per second. So that's velocity, 12 meters per second. And I'm going to include the right here. All right, what's its momentum? Well, that's just P equals mv, or you don't need me to do the substitution. That gives us 48 kilogram meters per second to the right. Easy enough. Next. There we go. Yeah, so here's a good one. A very common sort of question. Can a bullet and a bowling ball have the same momentum? So you, Maura, stop, think, maybe pause, Maybe just think right now as I'm babbling. And what do you think? Is it possible for a bullet and a bowling ball to have the same momentum? Well, it is possible. All right. So if we say bullet and bowling ball, all right, typically, when you think of a bullet, I think of something little with a small mass. And typically bullets travel fast. I represent that with a big velocity. And the question is, well, so for a bowling ball, that's typically a pretty big mass, but moves with a relatively much smaller velocity. So yeah, those could be equal, right? Like, I don't know, 1 times 100 could be equal to 20 times 5, right? So it's not necessarily things that always have more mass have more momentum, or things that have higher speeds always have more momentum. It really depends on how both of those factors, mass and velocity, combine. What do you think? Good? Good. Now, impulse. Here's something that has an absolute definition, and it's pretty darn important. I'll just leave that. Yeah. The definition of impulse is change in momentum. All right? We talk a lot about when things change. Okay, so that is the definition of momentum, or sorry, of impulse, and one that you want to have pretty firmly in mind. All right, so what do we have to do to change an object's momentum? Well, if we know that momentum is m times v, how can you change something's momentum? Well, it says you could either change its mass or its velocity. Now, typically, it's kind of difficult to change change something's mass. You have to break it, or I don't know how you do it. So what we usually say is change its velocity. All right, that's the most straightforward way to change something's momentum. Oh, right, by changing its velocity. Sorry. Good. So that gives us an equation for impulse. All right, since momentum is p and impulse is change in momentum, that means we can write impulse as delta p. There's change in momentum. All right, and I'm going to write it as mass times change in velocity. Fair enough? Now, impulse actually gets its own variable, capital J. It's also a vector because change in velocity is going to occur in some direction, and therefore change in momentum occurs in some direction. Okay? So an equation there you want to have a good handle on. It's all right? It's all right. Now this part, yeah, okay, we can do this. So, yeah, what do you have to do in order to change something's velocity, right? We're talking about impulse changing momentum. Well, to change momentum, we have to change velocity. And if there's let's say there's a cart that's rolling along one of our tracks, and I tell you to change its velocity, well, what are you going to have to do? Or really, I'm saying, if to change its velocity, I'm saying to make it accelerate, well, what are you going to have to do? Any idea? Make that cart accelerate more. You are going to have to apply a force. Right? That's what forces do. Forces make things accelerate. All right? Now, we came up with, well, Isaac Newton came up with an equation a couple hundred years ago, and he said that, I'll simplify it, F equals ma. Right? So we use that a bunch to relate force and acceleration. Now, if you look at this, we can rewrite acceleration by definition. Acceleration is change in velocity, right? There's that idea of changing velocity over change in time. All right? And if I go ahead and multiply both sides here by delta t, we're still using the same equation basically, but we're just writing it in a little bit different way. And what's nice here is look what we're left with, right? We're left with impulse. So here's another way to write impulse. F times delta t. So I'm going to put that right back up here. F times delta t. Again, F is a vector. The direction of force is real important. So here's one kind of big, long equation that we can use. All of those things are impulse, right? J is impulse. Delta P is, well, change of momentum. That's the definition of impulse. M delta V is one way of calculating impulse. F delta T is another way of calculating impulse. All right, so all those things are one big equation. And this part right here, this part, M delta V equals F delta T. Kids over the years have remembered that saying, saying fat equals mav, like those deltas become A's, or mav equals fat. So if that helps you remember that, super. Okay, so here's an example. All right, a 1,500 kilogram car traveling at 24 meters per second stops by applying its brakes over a period of 7.5 seconds. What impulse? Well, I'm going to write down some things we know. First, we know mass is 1,500 kilograms. Now this part, traveling at 24 meters per second, what's that, Maura? Yes, exactly. That's V initial, 24 meters per second. All right, what other clue do you see here that tells us something? Well, I'll just write down this T, right? We do know time, 7.5 seconds. And what other clue do you see in this question? What is it, Maura? You got it. It's stops, right? That means V final is 0. Okay, so we want impulse. Again, here are all sorts of ways to find impulse. And hopefully you can tell that we have two different velocities. That's going to allow us to do a delta V and a mass, so we can do M delta V. So I'm going to write that impulse is M delta V. I'm going to go one step farther by saying anytime we do a change in any quantity, we always do V final minus V initial. Okay, so I'll do this. Let's see. J is 1,500 kilograms times, now the delta V, VF 0 minus VI 24 is negative 24 meters per second. All right. I don't have a calculator, but I think that's 36,000 maybe? 36,000 kilogram meters per second, and it's negative. So let me do this. Try to sneak this in here. J is negative 36,000 kilogram meters per second. Why is it negative? Well, a couple of reasons. The big deal is because this thing loses momentum, right? Impulse is change in momentum, and this thing has its momentum decreases. It goes from moving to not moving. Therefore, its impulse, its change in momentum, has to be negative. All right. The other reason is, if you think about it in terms of this one, F delta T, well, I guess that's part B here, right? I'm going to sneak it up into this area. What average force is applied? Well, now we can say that we know J, we can call that equal to F delta T. So F is J over delta T, or negative 36,000 kilogram meters per second divided by 7.5 seconds. Now I really need a calculator. Here we go. 36,000 divided by 7.5. Yeah, so I get a force of negative 4,800 newtons. Now, what's a negative force? Well, you know, forces don't have negative values. The negative refers to the fact that this board is a real mess. But if the car was moving this way, right, well, what do we have to do to make it slow down? Well, you have to apply a force this way, right? That's the whole thing about moving one way, accelerating in the opposite direction. That's what makes you slow down, all right? So these negative signs here really refer to direction of the impulse, direction of the force. If I had written a better question, I would say something about that the car is traveling east at 24 meters per second. Then we could say the force is 4,800 newtons towards the west, or 4,800 newtons west. Make sense? Okay, so the homework sheet that's up on Headline, you're going to have trouble with one of the problems. number 4. All right, because that comes kind of from the lab. So don't worry about number 4 too much. Number 5 is like a 2-part problem. That'll be a little bit of a challenge there. But you're going to mix some free fall stuff with some of this impulse stuff. So and the first 2 hopefully shouldn't be too, or first 2 or 3 hopefully shouldn't be too bad if you're okay with that big formula here, the big formula here. Okay? All right, Maura. Get better. See you soon.